In 2023, the James Webb Space Telescope detected the infrared signature of water vapour around a rocky planet called GJ486b, just 26 light-years from Earth. The planet is scorching hot and orbits its star in less than 2 days, a place where any atmosphere should have disappeared long ago. Yet Webb saw water's unmistakable mark, raising one question: is it coming from the planet itself, or from the star it circles? If you're drawn to the unknown, subscribe and join the journey as we continue exploring the mysteries of the universe. When astronomers first catalogued the faint red dwarf star known as GJ486, it seemed unremarkable, one of the countless small cool suns that quietly fill the Milky Way. Red dwarfs burn at low temperatures and live unimaginably long lives. From Earth, this particular one glows far too faintly to see without a telescope, tucked deep in the constellation Virgo, about 26 light-years away. In 2021, a subtle, rhythmic dimming in that starlight betrayed the presence of a companion. Careful measurements revealed a planet roughly 1.5 times the size of Earth. It circles its host every 1.47 days, so close that its orbit would fit easily inside Mercury's path if placed in our own solar system. This compact world receives almost 70 times the energy Earth gets from the Sun. Its surface temperature hovers near 430 degrees Celsius, 800 degrees Fahrenheit, high enough to melt metals. From those numbers alone, researchers assumed they were looking at a dead, airless rock. Any atmosphere would have boiled away eons ago under that relentless radiation. Red dwarf stars are also notorious for their flares and magnetic storms, which blast surrounding planets with charged particles. Over time, those outbursts strip gases from a planet's surface like sand blown off stone. By all logic, nothing resembling air should remain here. Yet even a hostile world can tell a story. This particular planet, classified as a super-Earth because it's larger and heavier than ours but still rocky, offered a near-perfect laboratory for studying how small planets evolve around dim stars. With a density of about 7 grams per cubic centimetre, it's probably made of iron and silicate rock, much like Earth, but slightly richer in metal. If someone could stand there, gravity would press 3 times harder than it does at home. Every movement would feel slow and heavy, as though walking underwater. Because it lies so close to its star, the planet is almost certainly tidally locked. One side faces eternal daylight, the other endless night. The day side bakes under the glare of its parent sun, its rocks glowing a dull red. The night side never sees the star at all and may sit hundreds of degrees colder. Between them runs a narrow twilight zone where searing heat and deep cold collide. If even a wisp of atmosphere survived, ferocious winds could race from day to night, redistributing heat. Without one, the contrast would be absolute. Molten stone on one side, frozen silence on the other. Despite its extremes, this world turned out to be an ideal target for the James Webb Space Telescope. Each time it passes in front of its star, the system's brightness dips by a measurable amount. During those brief transits, a fraction of the starlight filters through whatever gases or bare vacuum surround the planet. By splitting that light into a spectrum, astronomers can detect faint molecular fingerprints. For decades, telescopes like Hubble and Spitzer attempted this feat but lacked the sensitivity to analyze such tiny, rocky worlds. They succeeded only with large gas giants, whose thick atmospheres produced obvious signals. Webb, with its 6.5-metre mirror and advanced infrared spectrographs, finally had the precision to probe smaller planets. No one expected this particular observation to reveal anything dramatic. In fact, it was chosen precisely because it shouldn't have an atmosphere. The plan was to use the planet as a control case, a simple, hot rock whose featureless spectrum could confirm Webb's ability to measure nothing. But nature often resists expectations. Before Webb began observing, teams on Earth studied the red dwarf itself. It's an M3.5 type star about a third the Sun's radius, glowing orange-red at roughly 3,300 Kelvin. It rotates slowly, taking over 4 months to spin once, which suggested moderate magnetic activity. Even so, red dwarfs are unpredictable. They erupt in bursts of ultraviolet radiation, their surfaces speckled with cool, dark star spots. Understanding that behavior was crucial. Light variations from the star can mimic or hide the chemical traces scientists hope to see. The first Webb observations came from the Near-Infrared Spectrograph, NIRSPEC, which collected light during several planetary transits. Each exposure was painstakingly calibrated to remove noise, detect drift, and cosmic ray hits. When the data were finally reduced, the main transit curve looked exactly as expected, a crisp dip showing the planet's passage across the stellar disk. Then analysts noticed something small but persistent in the residuals. Extra absorption centered near 1.4 microns, the specific wavelength where water vapor absorbs infrared light. At first, the team assumed an error. The effect measured only a few dozen parts per million, barely above the detection threshold. But when they processed a second transit taken months later, the same feature appeared in the same place. Statistically, the chance of random noise producing it twice was vanishingly small. If genuine, the implication was startling. Water molecules should not exist anywhere near such a scorched surface. The observation challenged everything scientists thought they understood about atmospheric loss around close-in rocky planets. Multiple teams reanalyzed the data independently, each using different algorithms to correct for stellar and instrumental effects. All arrived at the same conclusion. Something in the system was absorbing light exactly where water does. The question was where that water resided. One hypothesis placed it in a thin atmosphere continually replenished by volcanic activity. Deep inside, residual heat and tidal forces could melt rock, releasing steam through fissures and vents. That outgassing might sustain a faint envelope of vapor for millions of years, even as stellar radiation tore it away. Such a process occurs on Io, Jupiter's volcanic moon, though on a far smaller scale. Another idea involved the planet's surface itself. Some minerals trap water in their crystal structures. When heated beyond a certain point, that water escapes as gas, a process called thermal desorption. On the sunlit hemisphere, it could form a fragile veil of vapor, renewed each time the minerals reabsorb moisture from cooler layers during the night cycle. But both scenarios strain credibility. The star's intense radiation would quickly break water molecules apart and sweep the fragments into space. To maintain a detectable signal, release and loss would need to balance perfectly, second by second, across the entire surface. A third possibility shifted attention back to the star. In the cooler regions of a red dwarf photosphere, water vapor can form naturally. If the planet's transit path crossed one of those dark star spots, Webb would register the stellar water as though it came from the planet. The mimicry is nearly perfect. Even high-precision instruments struggle to tell them apart. Distinguishing between these explanations requires observations at additional wavelengths. Fortunately, Webb carries another instrument, NIRISS, that covers a slightly different infrared range. Comparing how the suspected water signature changes across those wavelengths could reveal its true origin. If the signal grows stronger towards shorter wavelengths, it's likely stellar. If it weakens, it belongs to the planet. Those follow-up studies were scheduled soon after the first results came in. Regardless of the outcome, the detection represented a turning point. It proved that Webb can see molecular features in the atmospheres or near-surface environments of Earth-sized planets. Before this, such sensitivity was unimaginable. Each observation teaches scientists not just about one world, but about the limitations and strengths of their own methods. The discovery also rekindled discussion about red dwarf systems in general. These stars make up roughly 70% of our galaxy's population. For years, many researchers considered them poor candidates for habitable worlds, citing their flares and the tidal locking of their planets. But new models suggest that with strong magnetic fields or constant volcanic activity, even close-orbiting super-Earths might retain thin atmospheres. If that's true, then the galaxy could be full of rocky planets, still holding traces of gas and water despite the odds. From a broader perspective, this single world serves as a crucial link in our understanding of planetary evolution. It bridges the gap between the giant planets, whose thick atmospheres are easy to study, and the small terrestrial worlds where signs of air are almost invisible. Whether or not it possesses water vapor, its data refine the techniques needed to analyze cooler, more temperate targets in the future. Science progresses by confronting contradictions. The unexpected hint of water around a planet that should have none forces theorists to reconsider how atmospheres behave under extreme radiation. Perhaps volcanic replenishment is more efficient than models suggest. Perhaps red dwarf flares erode gas differently depending on magnetic orientation. Each question becomes the seed of another study. When the observing campaign concluded, researchers archived terabytes of data and began planning deeper analyses, more instruments, more wavelengths, more time. Meanwhile, ground-based telescopes monitored the parent star's variability to quantify its magnetic cycles. The better they understand that small red sun, the clearer the planet's signal will become. For now, the truth remains unresolved. Somewhere in that distant system, a small rocky world continues its rapid orbit. One hemisphere glowing under unending daylight, the other frozen in darkness. Webb will watch again and again, catching the faintest whispers of light that reveal its secrets. Whether the water lies on the planet's surface, in its skies, or within the star that warms it, the discovery marks the beginning of a new era. The boundary between what we can and cannot detect has shifted. The technology works, the questions grow sharper, and as those photons from 26 light-years away arrive one by one, they carry with them a message far larger than a single world. Even in places where we expect nothing, the universe still surprises us. The anomaly appeared as a faint dip around 1.4 microns, a feature that water vapor produces in infrared light. The signal was weak, just a few dozen parts per million, but it remained after every calibration step. No matter how analysts adjusted Webb's detector models or removed instrumental drift, the feature persisted. Webb's near-infrared spectrograph had gathered thousands of exposures during 2 separate transits. When light from the star passed through the space above the planet, certain wavelengths dimmed slightly. Each absorption corresponded to a specific molecule interacting with that light. The challenge lay in separating genuine molecular fingerprints from the constant variability of a red dwarf star. Each research group used its own pipeline to process the data. Thermal corrections, background subtraction, and detector response maps differed, but all produced the same narrow trough in the spectrum. That consistency meant the signal was real. It existed in the incoming light itself, but the data offered no clue about location. Water could be suspended above the planet, or it could be mixed into the cooler layers of the star's photosphere. Timing analysis gave the first clue. True atmospheric absorption should appear only during transit and vanish immediately afterward. Stellar effects linger or drift as the star rotates. The intensity curve peaked within the transit window yet showed slight residuals afterward. enough to keep both options viable. To explore the stellar explanation, astronomers modelled the host as a patchwork of magnetic star spots. In these regions, temperatures can drop below 3000 Kelvin, cool enough for water molecules to form. A planet crossing such an area blocks less total light at the wavelengths where water absorbs, creating an apparent absorption feature in the combined signal. Simulations varying spot coverage from 1 to 10% reproduced the depth of the observed feature almost perfectly. Under certain conditions, the star alone could explain the data. Another model, using a planetary atmosphere just a few molecules thick, fit equally well. It required a global layer of vapour amounting to less than 1/10,000,000th of Earth's atmospheric pressure, tenuous but enough to alter the spectrum. Both scenarios fell within the uncertainty range of the measurements. Webb's precision had reached the point where two physically different realities produced identical curves. The next diagnostic was wavelength behaviour. Planetary water absorption weakens toward shorter wavelengths, while stellar water strengthens. Webb's NIRISS instrument covers exactly that range, from 0.8 to 2.8 microns. Observing additional transits with NIRISS would reveal the slope of the feature and with it its origin. Those observations were cued for the telescope's next observing cycle. Meanwhile, teams examined the feasibility of water surviving near such heat. Tidal forces keep the planet's interior molten. Volcanic vents could release steam continuously, replenishing a thin exosphere as radiation strips it away. Numerical models show that a balance between outgassing and loss might maintain trace vapour for thousands of years. Surface processes could also contribute. Hydrated minerals release water when heated above 400 degrees Celsius. On the sun-facing hemisphere, that reaction would occur constantly, generating a localized cloud of molecules above the crust. On the night side, the process would reverse, reabsorbing moisture into the rock lattice. The result would be a perpetual cycle of release and capture, driven by the planet's locked rotation. Calculations of escape velocity complicate that picture. At temperatures near 700 Kelvin, hydrogen atoms move fast enough to escape gravity entirely. Ultraviolet radiation from the star splits water molecules, and stellar wind carries the hydrogen away, leaving oxygen to oxidize the surface. Unless new vapor emerges continuously from below, the signature would fade quickly. A strong magnetic field could slow this erosion, but tidal locking likely suppresses internal rotation, the mechanism that generates magnetism. Without that protection, charged particles stream directly into the upper layers of any atmosphere, heating and dispersing it. The persistence of water would therefore require an improbable combination of intense volcanism and residual magnetic shielding. Attention returned to the star. Observations of similar M-type dwarfs show intrinsic water features, even without orbiting planets. The Hubble Space Telescope recorded identical absorption bands at 1.4 microns in isolated stars, confirming that water exists naturally in cool stellar atmospheres. If this red dwarf shares those properties, Webb's signal could easily originate there. Yet an atmospheric contribution from the planet cannot be ruled out. Mercury, though nearly airless, maintains a detectable exosphere of sodium and potassium, replenished by micrometeorite impacts and solar heating. Scaling that mechanism to a heavier world would yield a denser, short-lived cloud, precisely the kind of structure capable of producing a marginal water signature. Instrument specialists cross-checked the detectors for artifacts. The pattern survived every test. Background fluctuations, pointing jitter, even cosmic ray hits, none explained the feature. The photons themselves carried the signature. The question was whose environment they had passed through. Statisticians quantified confidence levels for both hypotheses. Planetary origin probability, roughly 45%. Stellar origin, about 55%. The margins changed with each assumption about spot coverage or atmospheric composition. In practical terms, the data could support either scenario equally well. Because of this ambiguity, new strategies emerged. Upcoming transits will be monitored simultaneously from space and from ground-based telescopes tracking stellar brightness variations. If the spectral feature correlates with surface activity on the star, the cause will be clear. If not, the remaining explanation will be an atmosphere, however slight. Engineers prepared adjustments to Webb's calibration routines to improve stability at micro-wavelength precision. Even tiny thermal oscillations in the observatory's mirror can shift measured absorption depths. Correcting those drifts will be critical when future targets, cooler, smaller, potentially habitable worlds, produce even weaker signals. The immediate goal is to capture several more transits under different stellar conditions. Comparing spectra during periods of high and low activity could isolate the effect of star spots. If the water signature changes with stellar brightness, it belongs to the star. If it remains constant, it points to the planet. New models incorporate three-dimensional mapping of the star's surface to simulate evolving magnetic regions. Synthetic spectra from these maps will be compared directly with Webb's next dataset. The approach should reveal whether the 1.4 micron feature results from spatial temperature variations or genuine molecular absorption around the planet. Every refinement adds another variable to track: instrument temperature, detector gain, pointing stability, stellar rotation phase, flare probability. The complexity is extreme, yet the prize is simple: a clear yes or no on the presence of water beyond our solar system. The final step before new observations begins with recalibrating NIRISS detectors to ensure cross-instrument accuracy within 1 part in 10,000. Once that is complete, Webb will observe consecutive transits, capturing spectra from 0.8 to 5 microns in a single sequence. Those measurements should display the full shape of the absorption band and its dependence on wavelength. Only then will it be possible to tell whether the faint trough in the data belongs to a planet venting steam or to the cool scars of a restless red dwarf. The measured signal strength implies that any layer of vapor must be thin, probably no denser than the wisps of gas surrounding Mercury. Such an exosphere would behave less like weather and more like a plume, constantly escaping, constantly renewed. Models show that even a pressure of a few microbars could scatter infrared light enough for Webb to detect it. The question is whether geology below the surface can supply gas fast enough to sustain that film against relentless loss. Tidal heating offers one potential engine. The planet's orbit is slightly elliptical. As it moves closer and farther from its star each cycle, gravitational forces stretch and relax its body. Friction from that movement converts orbital energy into internal heat, a process that can keep the mantle partially molten for billions of years. The same mechanism powers the volcanoes of Io, but on a world 3 times Earth's mass, the results would be far more dramatic. Magma chambers could extend deep into the interior, their surfaces venting through cracks tens of kilometers wide. If water or hydroxyl compounds are trapped in the mantle, those vents would release steam along with carbon dioxide and sulfur dioxide. Near the substellar point, outgassed material would instantly split under ultraviolet light. Hydrogen would rise and escape, while heavier fragments might linger as a temporary veil. The balance between venting rate and escape rate would set the planet's visible signature. Surface chemistry complicates the picture. At temperatures above 700 Kelvin, many minerals change structure. Iron oxidizes rapidly, silicates lose bound water, and sodium and potassium become volatile. Each process injects new species into the near-surface environment, contributing faint spectral lines that can overlap with water features. To interpret Webb's data, scientists must model not only atmospheric physics, but also high-temperature mineral reactions. The night side adds another variable. There, the temperature may fall below the condensation point of several gases. If residual vapor drifts across the terminator, it could freeze and re-enter the crust as hydrates or ice is embedded in regolith. Over time, this exchange would transfer volatiles from the hot hemisphere to the cold one, gradually altering surface composition. The efficiency of that transport depends entirely on wind speed and atmospheric density, both currently unknown. High-resolution general circulation models attempt to simulate these flows. They assume a tidally locked planet with a pressure of only a few microbars and use fluid dynamics equations to follow how vapor moves under constant stellar heating. The results show jets exceeding the speed of sound racing from the day side into darkness, cooling, condensing, and falling back toward the surface before re-evaporating. Even at minimal density, such motion redistributes material and affects emission spectra. The observed brightness temperature supports this idea. Secondary eclipse data reveal that the planet's dayside radiates at about 700 Kelvin, consistent with an airless or nearly airless surface, but slightly cooler than a perfect blackbody would be. That few percent difference could come from partial heat transport by trace gas or dust, lofted by micro-impacts. The distinction is small, yet measurable, and provides another clue about near-surface physics. Surface reflectivity adds to the story. The albedo, how much light the planet reflects, is estimated at less than 0.2, meaning it absorbs most of the incoming radiation. A dark basaltic crust fits that value. Laboratory measurements of molten basalt at similar temperatures produce nearly identical infrared emission curves. If Webb's future phase curve observations confirm this, it will mark the first remote identification of lava flows on a rocky exoplanet. Gravity on this world is about 3 times Earth's, so molten rock spreads in broad plains rather than tall cones. Viscous flows hundreds of kilometers long could cross the substellar hemisphere before solidifying. Continuous resurfacing would erase old craters and maintain a relatively smooth terrain. Over geological time, heavy elements might segregate toward the core, enriching the crust in lighter silicates. Another subtle difference that could influence spectral colour. Radiation from the parent star is intense, but primarily in the infrared. Only a fraction appears in the ultraviolet range that drives photochemistry. Paradoxically, that may help small amounts of water persist slightly longer. With less UV flux to break molecules apart, photolysis slows, though stellar flares periodically spike emission to destructive levels. These flares occur on weekly timescales, each one potentially sweeping away part of the exosphere. Monitoring those outbursts is essential for interpreting Webb's readings. Ground-based observatories equipped with high-cadence photometers track the star's brightness continuously. When a flare coincides with a transit, it alters the baseline illumination, creating artificial spectral shifts. Correcting for those effects requires synchronized observations across multiple wavelengths. Data from the Las Cumbres Observatory Network and the TESS spacecraft are being used to map the star's activity cycle in real time. The interior structure of the planet remains theoretical, but follows from density and mass. Models indicate an iron core comprising roughly 60% of total mass, surrounded by a silicate mantle and a thin crust. Core temperatures may exceed 5,000 Kelvin, hot enough to maintain partial fluidity despite age. If convection still occurs, it could generate a weak magnetic field, though tidal locking likely limits rotation to 1 full turn per orbit. The resulting field, if any, would be asymmetric, stronger near the terminator where motion persists, and weaker under the static substellar point. Such asymmetry could influence atmospheric escape. Charged particles follow magnetic lines. Uneven shielding means localized erosion, carving invisible channels through which gas escapes more efficiently. Detecting that pattern indirectly through variations in spectral intensity is one of Webb's long-term goals. The planet's gravitational grip on its star produces a measurable wobble, allowing radial velocity instruments on Earth to refine its mass and orbital shape. Combining those data with Webb's transit measurements gives a mean density precise to within 5%, an accuracy unheard of a decade ago for such small worlds. That precision constrains theoretical models of composition and evolution, narrowing possible scenarios for how the planet formed. Formation pathways around red dwarfs differ from those around Sun-like stars. Protoplanetary disks around small stars are compact and metal-rich. Planets forming close in can accumulate dense cores quickly before gas dissipates. This world likely assembled from refractory materials, iron, nickel, silicates, within the first few million years of the system's life. Any initial envelope of hydrogen and helium would have been stripped away early, leaving the naked core we see today. Residual water might have arrived later through impacts by volatile-rich planet Essimals migrating inward. If those impacts occurred after the star's most violent youth, some of the delivered water could have survived temporarily in mineral form. Geological recycling through partial melting and venting would then account for the present-day trace vapor signature. To test these scenarios, scientists run coupled thermal evolution and volatile loss models. Each simulation tracks mantle, temperature, degassing rate, and stellar flux over billions of years. The output predicts when outgassing stops, when crust solidifies, and what species remain detectable. For this planet, the models cluster around two outcomes. Either continuous low-level volcanism maintains a short-lived steam envelope, or complete atmospheric loss occurred billions of years ago, and only surface sublimation remains. Infrared phase curve data collected during non-transit periods provide additional constraints. By measuring the planet's brightness as it moves behind the star, astronomers can infer how efficiently heat spreads. A sharp drop indicates little redistribution, consistent with an airless rock. A gradual decline implies atmospheric circulation. Early measurements lean toward the former, but still allow a few percent deviation, enough to keep the debate open. Detecting emission from specific molecules other than water could help. Carbon monoxide, carbon dioxide, and sulfur dioxide each absorb at unique wavelengths. Their presence would signal active volcanism, strengthening the case for an atmosphere. The challenge is signal strength. The expected absorption depths are less than 20 parts per million, near Webb's current limit. Achieving confirmation will require stacking data from dozens of transits. Work is already underway to combine Webb's readings with observations from ARIEL, the upcoming European exoplanet mission optimized for atmospheric studies. Ariel will observe hundreds of planets, including this one, using complementary wavelength coverage. Joint analysis between the two observatories should reveal whether the 1.4 micron feature corresponds to isolated water vapor or a broader mix of volcanic gases. Spectroscopic time series will also track potential variability. If the vapor layer originates from active regions, its strength could fluctuate as new vents open or close. Detecting such changes would provide direct evidence of geological activity, the first of its kind beyond the solar system. Surface temperature mapping through secondary eclipse photometry offers another route. Small shifts in infrared emission across successive orbits could indicate transient hotspots. These would suggest lava lakes or fissures consistent with volcanism. No such variability has yet been confirmed, but upcoming observations at longer wavelengths will improve sensitivity. Gravitational interaction with any undetected companion planets could maintain orbital eccentricity and, by extension, tidal heating. Radial velocity monitoring continues to search for that companion. Even a body half Earth's mass in a nearby orbit could pump enough energy into the main planet to keep its interior partially molten. Every new dataset tightens the web of possibilities. The emerging picture is of a massive, metal-rich world enduring constant stress, its surface reshaped by heat and radiation. Traces of vapour hover above, fleeting and fragile, yet visible across trillions of kilometres. Whether that vapour belongs to the planet or merely to its star, it provides a benchmark for the limits of atmospheric survival. The next step depends on the NIRI-SS follow-up. With extended wavelength coverage, the slope of the absorption feature will reveal whether it weakens or strengthens toward shorter light. Combined with simultaneous monitoring of stellar brightness, this will pinpoint the source of the water signature. Instrument teams are finalizing calibration checks, aligning detector gains, and verifying thermal stability before those critical observations begin. Until that data arrives, the best evidence points to a narrow equilibrium, volcanic release competing with stellar erosion, surface minerals feeding the exosphere as quickly as space empties it. Every molecule that Webb detects is transient, part of a continuous exchange between rock and sky on a world where neither can rest. Follow-up transits are planned with overlapping instruments so that every photon can be traced back to its source. Webb's near-infrared imager and slitless spectrograph will extend the spectral range down to 0.8 microns, overlapping the region where water's absorption begins to taper. The goal is to chart the exact shape of the feature. If the depth of the trough decreases towards shorter wavelengths, the vapour belongs to the planet. If it increases, the culprit is the star. The distinction hinges on a slope measured to within a few parts per million. During each observation, Webb records the system's brightness across thousands of narrow wavelength bins. The resulting light cube contains not only the transit itself, but subtle temporal variations caused by the star's surface. By analysing how the absorption feature evolves minute by minute as the planet crosses different regions, astronomers can build a two-dimensional map of the star's temperature distribution. A constant signal across the transit favours a planetary origin, a fluctuating one reveals stellar heterogeneity. To validate those findings, ground-based telescopes monitor the star simultaneously in visible light. Star spots are darker in the optical range, so any dip in infrared absorption coinciding with optical dimming identifies a stellar source. Coordinated campaigns involving observatories in Chile, Spain and Hawaii are scheduled to capture these windows. The datasets will later be merged so that every spectral frame from Webb has a matching measure of the star's brightness and colour at the same instant. Cross-instrument calibration is critical. Even a 1% offset between NIRSPEC and NIRISS could distort the slope of the absorption line. Engineers at the Space Telescope Science Institute have spent months refining flat field corrections, verifying that detector temperature remains stable within a few thousandths of a degree. Thermal breathing of Webb's mirrors can subtly change focus. Periodic adjustments compensate for these shifts before each transit sequence begins. The new observations are designed to last longer than the earlier ones, capturing the system for several hours before and after the transit. Those baseline intervals allow measurement of stellar variability unrelated to the planet, establishing a reference spectrum. Subtracting that baseline from in-transit data isolates the component truly linked to the crossing. In parallel, spectropolarimetric studies from ground facilities such as CFHT and HARP-Zen are mapping the star's magnetic topology. Polarization signatures reveal the orientation and strength of surface magnetic fields, which correlate with the number and location of cool spots. Feeding that information into radiative transfer models produces synthetic spectra of the star at each rotation phase. Comparing those with Webb's results will show whether spot-induced absorption can fully explain the observed water band. Stellar rotation adds another variable. The host completes a full turn roughly every 4 months. Because the planet transits every day and a half, Successive crossings sample slightly different longitudes. Over several weeks, Webb will effectively scan the star's surface strip by strip, aligning the strength of the 1.4 micron feature with rotation phase can reveal periodicity characteristic of spot modulation. If the feature waxes and wanes with that period, it belongs to the star. If it remains steady, it must come from the planet's immediate environment. Flare monitoring continues through the TESS satellite and radio observatories. Ultraviolet bursts inject temporary water signatures into stellar spectra. By cooling expanding plasma, catching one during a transit could mislead analysis. Real-time alerts from TESS allow observers to flag and discard data affected by flares before combining exposures. The statistical framework for disentangling star and planet relies on Bayesian inference. Each hypothesis, stellar contamination or planetary atmosphere, is represented by a model containing dozens of parameters: spot coverage, temperature contrast, atmospheric scale height, molecular abundance, and noise terms. Using Markov chain sampling, computers generate millions of synthetic spectra and compare them with observations, updating probabilities with every iteration. The preferred solution is not the most dramatic, but the one that minimizes residuals across all wavelengths simultaneously. Early trial fits with existing data leans slightly toward a stellar explanation, producing marginally smaller residuals, yet the difference is within the uncertainty of detector calibration. That means definitive classification awaits the NIRI-SS results. Understanding stellar contamination has broader consequences. Red dwarfs dominate the galaxy, and their surfaces are far more complex than the Sun's. Star spots, faculae, and flares alter apparent transit depths at the 0.1% level, precisely the amplitude of atmospheric signals astronomers hope to detect on Earth-sized planets. Without accurate models of these effects, even the best telescopes will misinterpret data. This system therefore serves as the calibration standard for the entire field. Laboratories on Earth are reproducing similar spectra under controlled conditions. High-temperature furnaces simulate red dwarf photospheres, while gas cells filled with water vapor provide reference absorption lines. Comparing those to Webb's measurements refines molecular line lists used in atmospheric retrieval codes. The better the laboratory data, the more precisely astronomers can tell planetary air from stellar features. Infrared photometry also contributes. By observing the secondary eclipse, the moment when the planet moves behind the star, Webb isolates the star's pure light. Subtracting that from combined light measured before the eclipse reveals the planet's own emission. Any residual water feature present in both signals must originate from the star. A feature that disappears during eclipse belongs to the planet. Executing this comparison demands timing accuracy within seconds and stability across orbits lasting days. To maintain that precision, mission controllers schedule observations during periods of thermal equilibrium, when sunlight on Webb's sunshield remains constant. Variations in telescope temperature can mimic small spectral changes. Every adjustment of pointing or orientation introduces minute heating. Calibration observations before and after the transit correct for that effect. If nearest confirms the feature weakens at shorter wavelengths, analysts will proceed to quantify atmospheric properties. Retrieval algorithms translate absorption depth into scale height, the effective thickness of the gas layer. Assuming water dominates and temperature matches dayside brightness, the inferred pressure would be less than 1/10,000th of Earth's. At such density, molecules would collide infrequently. The boundary between atmosphere and space would blur. Detecting any signal under those conditions would underscore Webb's sensitivity. If, on the other hand, the slope strengthens, the signal must arise within the star. That outcome would have equally valuable implications. It would provide the first direct measurement of water in a red dwarf photosphere and offer constraints on convection and magnetic mixing inside these cool stars. Stellar atmosphere models currently struggle to reproduce molecular opacities at low temperatures. Webb's data could resolve that uncertainty. Parallel analyses will compare line widths of the suspected water band with those of known atomic features. Planetary absorption, broadened by motion through the atmosphere, produces symmetrical lines. Stellar lines, shaped by turbulence and magnetic fields, skew slightly. Measuring that asymmetry requires signal-to-noise ratios exceeding 1000, challenging but achievable after stacking multiple transits. Machine learning classifiers trained on simulated spectra are being deployed to automate this separation. Networks learn the subtle correlations among multiple wavelength bands that distinguish planetary and stellar water. Once validated, these models can process future datasets from other systems in hours rather than weeks, accelerating discovery. Beyond Webb, upcoming missions will exploit what this case teaches. The Aerial Observatory will observe hundreds of exoplanets using dedicated time series optimized for atmospheric retrieval. The methodology refined here, multi-wavelength slope analysis, simultaneous optical monitoring, and stellar surface mapping, will form Aerial's standard protocol. The planned Habitable Worlds Observatory will extend it further into direct imaging, where reflected light rather than transits reveals composition. Back at the analysis level, each new dataset adds to a cumulative likelihood function describing both scenarios. As additional transits are processed, the curve representing planetary origin may rise or fall gradually until one hypothesis overwhelms the other. Scientists expect decisive separation once total observing time exceeds about 50 hours, a threshold reachable within Webb's second extended mission. The implications reach well beyond this single target. Distinguishing star and planet in spectra, this feint defines the frontier of current instrumentation. The process reveals how photons encode overlapping layers of information. One from the star's convective surface, one from the planet's thin exosphere, and one from interstellar space itself. Understanding how to disentangle them will determine the success of every future search for life-related molecules. Preparations for the next observation sequence continue. Telescope operators rehearse pointing maneuvers, engineers monitor detector temperatures, and software teams update retrieval codes with improved molecular constants. When the window opens, Webb will lock onto the star again, capturing continuous spectra for nearly 10 hours. Each photon that arrives will carry within it a history of collisions between light and matter, between data and doubt, waiting to be decoded. The final confirmation of origin will depend not on a single measurement, but on convergence across instruments. Only when the NIRISS slope, the optical light curves, and the phase curve thermal data all agree, will scientists declare whether the water signal arises from the planet's thin atmosphere or from the star's cool scars. Until that synthesis is complete, the distinction remains blurred. Two overlapping spectra, two environments, one faint molecular signature threading through both. Whether the water belongs to the star or the planet, the investigation has already reshaped how astronomers study small worlds. Before this campaign, infrared spectroscopy on rocky exoplanets was largely untested territory. Instruments were built with gas giants in mind, worlds 100 times larger, wrapped in deep, easily measured atmospheres. Extracting a signal from a planet barely 1.3 times Earth's radius required precision never before attempted. Every photon collected from this system teaches engineers how to reach that precision again and more efficiently on future targets. Rocky planets around red dwarfs form the majority of potential Earth analogues within reach of present technology. These stars are small, cool, and faint, so their planets must orbit close to receive comparable warmth. That geometry increases the chance of transits and shortens orbital periods, allowing frequent observations, but it also exposes the planets to intense radiation and magnetic activity. The data streaming from this system serve as a stress test for the theory that life could emerge near such volatile suns. If a world enduring 800-degree temperatures can retain even a wisp of vapour, then cooler planets in similar systems might preserve oceans. The outcome will inform models of atmospheric escape. At the heart of those models lies a contest between gravity pulling gas downward and stellar energy pushing it away. Ultraviolet photons from the star break apart molecules high in the atmosphere. The resulting hydrogen atoms, light and fast, reach escape velocity and stream into space. Over billions of years, this process can strip an entire planet bare. Quantifying how much radiation a planet endures before it loses everything defines a critical threshold, the atmospheric survival line. The new data help locate that line for rocky planets, showing whether mass alone can offset stellar violence. Planetary scientists feed these numbers into global circulation models, the same kind of physics engines used for climate prediction on Earth. By adjusting parameters such as surface gravity, albedo, and magnetic field strength, they can simulate thousands of possible worlds. The simulations predict how temperature and pressure evolve with altitude, and how quickly gases are lost. When the model reproduces Webb's measured spectrum, it reveals what combination of conditions could have produced it. Each simulation narrows the range of plausible realities. The discovery also affects how astronomers interpret flat spectra, those nearly featureless plots of light that often emerge from transit studies. In the past, a flat line was taken as evidence for a cloud-covered or airless planet. Now it may also signify stellar interference. Observers can no longer treat stars as static light sources. They are dynamic, molecularly complex surfaces. Accounting for that complexity will refine every future measurement. Understanding red dwarfs has become one of the top priorities in exoplanet astronomy. They make up roughly 70% of all stars in the Milky Way, yet their detailed spectra are still imperfectly modelled. Their temperatures hover near the condensation point of many molecules, so features from water, carbon monoxide and titanium oxide overlap in tangled patterns. Laboratory spectra collected on Earth rarely extend to the high pressures and magnetic fields found in stellar photospheres. The calibration provided by Webb's data offers the first real benchmark for these environments. At the same time, planetary geologists are revising ideas about internal heat and outgassing. A world 3 times Earth's mass retains its primordial heat longer, and higher pressure at the core keeps parts of the mantle molten for billions of years. Volcanic activity could therefore be ongoing even under the planet's solidified crust. If so, volcanic plumes might inject water vapour, carbon dioxide, or sulfur gases into a transient atmosphere. Observing similar signatures on other super-Earths would support this interpretation. It would mean that despite surface infernos, their interiors remain restless, capable of rebuilding atmospheres long after stellar winds destroy them. Measurements from the secondary eclipse campaign have already supplied vital boundary conditions. The planet's dayside temperature, hovering near 865 degrees Fahrenheit, corresponds almost exactly to a bare rock under direct stellar illumination. That finding limits any potential atmosphere to a pressure less than 1% of Earth's. In practical terms, it means that if an atmosphere exists, it must be extremely thin and probably short-lived. Yet detecting it at all suggests continual replenishment. Geophysicists calculate how rapidly volcanic degassing would need to occur to balance the loss. The result, 10 to 100 times Earth's current volcanic flux, sounds extreme but is physically plausible for a young, massive planet. Such a balance between loss and supply could produce a steady-state atmosphere, neither stable nor vanishing, but endlessly cycling. For astrobiology, this is significant. A thin atmosphere may seem inhospitable, but it still affects surface chemistry. Ultraviolet radiation breaking apart water molecules generates free oxygen atoms that can oxidize minerals, altering reflectivity and infrared emission. These reactions can be detected remotely, offering indirect clues about geological activity even on planets too hostile for life. From an observational standpoint, the system demonstrates how minimal the signal from a rocky planet can be. During transit, the total drop in brightness is less than 0.01%, and the absorption features are smaller still, tens of parts per million. Detecting them requires removing instrumental noise, pointing jitter, cosmic ray hits, and thermal drift with surgical precision. Every correction technique refined here, such as decorrelating spectral channels with spacecraft temperature and eliminating time-dependent bias, will feed into the pipelines used for future missions. These lessons arrive just as astronomy prepares for a new generation of telescopes. The extremely large telescope in Chile and NASA's Roman Space Telescope will soon join the search for rocky worlds. Their instruments depend on knowing how stellar variability contaminates spectra. Without that knowledge, direct imaging campaigns could misclassify spots on stars as planetary signatures. The dataset from this 26 light-year neighbour becomes a reference manual, a calibration point for every exoplanet study that follows. The implications extend to planetary formation itself. Discovering water, even transiently, on such a scorched world hints that volatile compounds survive deeper within rocky planets than models once assumed. When planetary embryos form, water can become trapped in silicate minerals or iron hydrides inside their mantles. Later, as the interior differentiates, that water is released through volcanism. Understanding how much remains bound versus lost informs estimates of initial water budgets for all terrestrial worlds, including Earth. Astronomers are also reassessing how they define a planet's habitable zone. Traditionally, it's the region where liquid water could exist on the surface, but habitability depends as much on atmospheric retention as on temperature. If radiation from a red dwarf strips away air faster than a planet can replace it, even a perfectly temperate orbit will yield a lifeless rock. This realization pushes the inner edge of the habitable zone outward and may shrink the number of truly viable systems. The present observations provide the empirical anchor for that recalibration. Inside data archives, teams analyze every photon again using independent methods. One group fits parametric models to remove stellar noise. Another applies machine learning algorithms trained on synthetic spectra. When all approaches converge on the same parameters, confidence grows. Disagreement triggers deeper investigation of systematics. The process illustrates how modern astrophysics functions, not through single eureka moments, but through iterative refinement by hundreds of specialists across continents. Even if the final verdict declares the water stellar, not planetary, that outcome resolves more than it disappoints. It would confirm that red dwarfs can harbour cool, molecule-rich regions on their surfaces, miniature laboratories for chemistry that could influence planetary climates. When star spots cover a significant fraction of the surface, they change the spectrum of radiation reaching nearby planets, potentially affecting atmospheric photochemistry. Future models of habitability around M-type stars will incorporate this effect directly, thanks to these measurements. Instruments designed for Webb's successors are being modified accordingly. Detector arrays now include redundant temperature sensors to monitor subtle drifts, and calibration lamps cover the exact wavelengths where red dwarf molecules absorb. The objective is to make future data less ambiguous from the outset. By learning from this challenging case, engineers reduce uncertainty for everything that follows. The collaboration behind the project spans more than 24 institutions. Data analysts in Arizona coordinate with modelers in Geneva and hardware specialists at Goddard. Each group focuses on a different piece of the puzzle: stellar magnetism, molecular spectroscopy, thermal emission modelling. When they exchange intermediate results through shared servers, discrepancies often highlight the next step. A mismatch between predicted and observed line depths might reveal missing opacities in databases or underestimated detector noise. Progress unfolds through these cross-checks rather than through grand revelations. The philosophical impact is harder to quantify but equally real. Every time a faint absorption line is confirmed or dismissed, humanity's view of its neighbourhood sharpens. The detection of water near a planet 26 light-years away doesn't change daily life, yet it redefines what counts as nearby and reminds us how fragile atmospheres are. Worlds can lose theirs entirely. Earth could too, given different circumstances. Observing that process elsewhere gives context to our own planet's balance between radiation, gravity, and life. Funding agencies watch closely because these results justify missions worth billions. Demonstrating that Webb can detect molecular features on rocky worlds opens the path for dedicated atmospheric telescopes. Confirming that stellar contamination limits sensitivity in certain regimes directs resources toward complementary techniques such as high-resolution ground spectroscopy or direct imaging. Either conclusion accelerates the field by clarifying where to invest next. Students entering astronomy today will treat this case as their first example of data interpretation under uncertainty. They will learn that ambiguity is not failure, but a stage in discovery. A signal that might belong to a star or a planet forces the community to improve instruments, revise models, and observe again. That cycle, observation, doubt, refinement, is the foundation of empirical science. Meanwhile, theorists use these constraints to explore extreme chemistry. At 800 degrees Fahrenheit, silicates begin to vaporize, releasing sodium and iron into any surrounding gas. A trace of water could interact with those vapors to form exotic hydroxides. Such reactions influence the opacity of the upper atmosphere, changing how much heat escapes. Including these interactions in models will produce more realistic predictions for superheated rocky worlds everywhere. Geophysicists also look at the planet's tidal locking for clues about interior dynamics. The perpetual day-night divide concentrates stress along the terminator line. Numerical simulations suggest that this gradient can drive mantle convection patterns unlike any on Earth, potentially focusing volcanism along a continuous ring. If true, the planet might vent gas preferentially near that twilight zone, replenishing atmospheric vapor in a steady plume rather than global eruptions. Future infrared phase curve observations could test this by searching for localized hotspots. Even chemistry within the star gains new relevance. If cool regions on the stellar surface truly contain water, it implies the presence of oxygen and hydrogen reservoirs deeper in the stellar atmosphere than models predict. That finding would influence our understanding of stellar evolution, magnetic field generation, and even the spectra of distant galaxies dominated by similar stars. Thus, whether the signal is planetary or stellar, it feeds back into cosmic models at every scale. Each observation adds another line to humanity's growing catalogue of exoplanetary environments. Some are wrapped in thick hydrogen envelopes, others bare and metallic, others still with ambiguous traces like this one. Together they form a continuum showing how planets evolve under different stellar conditions. The more examples we have, the better we can infer where Earth fits within that continuum. As data accumulate, the conversation among scientists has shifted from "is there water?" to "where can water survive?" That question drives mission planning for the next decade. The answer depends on stellar type, planetary mass, magnetic field, and distance, all variables measurable with current or near-future technology. Each parameter space mapped brings the long-term goal closer, identifying a truly Earth-like world with stable, life-supporting air. In the control rooms and laboratories analysing the system, researchers are already preparing to apply the same methods to cooler planets orbiting quieter stars. Those observations will reveal whether the boundary between airless and atmospheric worlds lies at a particular level of stellar activity or planetary gravity. Once that boundary is known, statistical surveys can estimate how many habitable worlds the galaxy actually contains. The search continues because the reward, understanding the conditions that make planets breathe, transcends any single discovery. Whether this rocky neighbour carries a transient veil of steam or only reflects moisture from its star, it has already shown how delicate the balance is between heat and gravity, between survival and loss. Each measurement refines that balance, inching science toward the point where numbers become knowledge. If you like the video, don't forget to leave a like. It makes a huge difference and helps the channel grow.